Lutetium is the heaviest and rarest stable lanthanide. It represents only 0.4% of the rare earth oxide content in southern Chinese ion adsorption clays. Securing 1 metric ton of lutetium oxide requires processing 250 metric tons of raw rare earth oxides. This extreme physical scarcity is compounded by geopolitical concentration. China controls 93% of global refining capacity for 5N-grade lutetium oxide. The purification process requires up to 1,000 stages of continuous countercurrent solvent extraction. This hydrometallurgical separation relies on hazardous organophosphorus solvents to isolate lutetium from adjacent ytterbium and thulium. The high chemical complexity and environmental footprint prevent rapid capacity duplication outside of China. The upstream supply chain is a near monopoly. Global demand for 5N lutetium oxide is expanding rapidly. Consumption grew from 12.5 metric tons in 2018 to an estimated 25.5 metric tons in 2024. This represents a 12.6% compound annual growth rate. This demand is directly coupled to the medical imaging market. A single positron emission tomography scanner requires up to 150 kilograms of scintillation crystal. Global scanner shipments reached 2,650 units in 2024. Inelastic supply has triggered an extreme price response. The market price for 5N lutetium oxide surged 190% between 2020 and 2024. Prices peaked at $1,600 per kilogram due to structural deficits and export anxieties. Securing raw lutetium does not resolve the downstream manufacturing bottleneck. Growing scintillation crystals via the Czochralski method requires temperatures of approximately 2,050 degrees Celsius. This extreme thermal environment limits crystal boule yields to between 38 and 45%. Thermal stress cracking and stoichiometry drift cause high scrap rates. Furthermore, the process requires iridium crucibles, which are the only vessels capable of withstanding these temperatures. These crucibles experience up to 1.8% material loss per run, escalating capital costs. These physical constraints have severely delayed medical hardware production. Average lead times for detector modules tripled from 16 weeks in 2020 to 48 weeks in 2024. The bottleneck is fundamentally metallurgical and thermal, resisting simple software or logistical workarounds.